our KPPC Kuwait Public Policy Lecture Series. A warm welcome to our dear friend, Dr. Pal Jeremy, who is a professor and a graduate program director in the Department of Civil Engineering and Environmental Science at Loyola Marymount University. Dr. Pal has over 25 years of experience in the field of climate change and its impact on water, resources, and the hydrological cycle, extreme climatic events including flood, drought, and heat waves, agriculture, and human health. He was also a member of the Intergovernmental Panel on Climate Change, which was a co-recipient of the Nobel Peace Prize in 2007. Today's lecture series is going to focus on climate change and its potential impacts on arid regions. So just to give you a quick background about the lecture, Dr. Pal will present the current state of knowledge of climate change and highlight the use of high-resolution regional climate models to make future climate change projections and assessments. He will show that the Arabian Gulf and the Red Sea regions stand to directly benefit from aggressive measures to mitigate climate change. Without any further ado, let us warmly welcome Dr. Jeremy Pal, which came all the way from California to lecture you today and inform you about the state of climate change. Dr. Jeremy, please.
Thank you. Can you hear me okay? Microphone's working? Okay. Well, first of all, I'd like to thank those who invited me here today, Ms. Futhe, and Mr. Faris and Ms. Fatima, and also His Excellency Dr. Khalid. So as was stated, I'm going to talk about the basic understanding of climate change and its potential impacts on arid regions. I'm going to focus in on human health, and as well as water resources. And I learned in preparing this presentation for the water resources side that we in California share many water issues, that we have many water issues in common. So I thought that share some of the things that we're doing in California to combat our water crises that we're facing. This presentation is really sort of three in one. So I'm going to actually, so they're all sort of mini presentations, and the first part will just be a basic climate change overview and the current state of the climate, as well as then we'll go into human health and heat stress in Southwest Asia, and then finally into water resources in arid regions, again, focusing on Southern California and then translating those issues to here in Kuwait. So let's start with the climate change overview. So why are we having this talk? It's simply because of these three curves. These are our greenhouse gases. These are our gases that trap heat in. I think that might be better. They're heat-trapping gases, so the sun warms the planet, then the planet then emits radiation into the atmosphere, and these gases then trap or hold the heat in. Because these have increased over the last 100 years or so, our concern is what is that impact on climate. This is a time series from 1880 to 2018, just got the latest data in of global temperature, globally average temperature. And you can see the last 5 years there. Microphones give you some problems. The last 5 years there have been the warmest on record. And we can also separate out different types of events. El Nino is a global forcing that tends to heat the climate. It's from the oceans. We have warmer oceans in the Eastern Pacific that then tend to be a source for heat in the atmosphere. And we can also pull out the La Nina years, which is colder than normal ocean temperatures, which tend to result in a cooling. And you can see that actually the La Nina and El Nino events are really the bounding, so they sort of bound our natural variability within the climate. But you can see a clear trend upward of warming. This is very indisputable. Okay. In fact, just a few statistics here. 20 of the warmest years have occurred in the last 22 years. And the last colder year when I was a child was in 1976. So it was the last year below normal there. Okay. These are temperature trends. We can see that this is impacting us at a global scale. There are regions that are more sensitive to others. And I guess to focus in two regions, one is the southwestern United States or Southern California, and we see tend to be a larger than normal warming. And also if we look at the Middle East or Southwest Asia, we see also warming that tends to be higher than the global average. So we've seen in both of the regions about 1 to close to 2 degrees of warming which is larger compared to the global average, which is around 1 degree warming. We've also, so that warming has caused our land ice to decrease. This is from 2002 when these satellites were launched into space, and we see that our land mass is significantly decreasing, or has been decreasing, probably much further before this, but these satellites came on in around 2002. That melting land ice has caused our sea levels, partially caused our sea levels to rise due to the meltwaters, but also due to the thermal expansion of the oceans. And we can see that globally we've had about a 1/4 meter of sea level rise. Okay, so that's sort of the basic state of the climate. I was very, very brief, but we need to make projections about future climate change. What are the potential impacts in the future? We do that using what are called global climate models. A global model takes the globe and essentially breaks it up into a bunch of grid boxes. There's a large mesh, a three-dimensional mesh, which we can see here. And all the processes, the key processes in our Earth system are represented. We have the land surface, atmosphere, oceans, ice, and so on. And each one of those grid boxes, for example, if you're in the atmosphere, you simulate processes related to advection or movement of air, diffusion, radiation, so light coming through and long-wave radiation bouncing around, and as well as the cloud and precipitation processes. And at the surface, we have all the key processes there. The land surface, the vegetation type. Here we might have a desert or semi-desert. The biosphere, you have ice or snow that can be simulated, runoff, all the hydrologic processes and the energy budget. This picture here is just a simulation of a model. All it's showing there is cloud cover. Okay, and we can see that that looks very much similar to maybe a satellite map that you would see in the Weather Channel or something. Okay, these models are used to simulate a variety of processes, and you can use them for experiments. So our control experiment might be a climate that has an Earth system that has greenhouse gases fixed at their pre-industrial level, and our perturbation experiment would be with our greenhouse gases changing or something. Okay, and then we look at the difference between the two. Okay. And that's how we make projections about the future. These computers are extremely, these models are extremely computationally expensive. They're run usually on supercomputers. So one of my collaborators, which I didn't mention at the beginning, Motasim Ashfaq, he works at Oak Ridge National Labs. This is the recently released computer that they have there. It's called Summit, and some of the simulations we'll be doing in the future will be on those, and then we have done previous simulations on the previous version. I also should acknowledge Dr. Elta here from MIT, and Brianna Pagan, who's from the University of Ghent University. Okay. And how well do these models perform? Well, this graphic is a very important graphic that came out of the 2013 IPCC report, and it gives a demonstration of how well the models perform. It's a little complicated, but with this black line right there, those are the observations. So this is essentially what our climate has done in the past. And if we look at the pink area there, that's all the these global models that we have in the world. There's about, let's call them 30 of them or so. And they include the natural forcings, which could include, say, a volcanic eruption or something like that, as well as the human forcings, which include the changes in greenhouse gases. And what we can see there is that the models over, in this case, global land surface temperature, the models do a very good job of capturing the historical observations. This purple area are the models without changing the greenhouse gases, so leaving the greenhouse gases at pre-industrial levels. So there's really two take-home points with this plot here. Is one, that the models do a very good job of simulating historical climate, at least at the global scale, which I'm showing here. But they also, they cannot simulate historical climate without changing the greenhouse gases. So there's very two important points there. We can look at that at a regional scale. And we can see that in all of the regions, the pink area, so the model with natural and anthropogenic human forcings are simulating the past climate. Unfortunately, the Middle East or Southwest Asia they never have a good region for it. So it's, it kind of fits in the Asia or the European region there, but you can see that the models do well in those regions. Okay, so we're making these projections about climate, but we don't know what we're going to do in the future. Are we going to continue on a business as usual track, so continue to emit on our current course, or are we going to mitigate something to what was agreed to in the Paris Agreement? And this is carbon dioxide. These are kind of carbon dioxide concentrations for the last 800,000 years from ice core data. And you can see at our current level, at just above 400 parts per million, we're well above that sort of natural variability range, and our carbon dioxide concentrations are much higher than we've seen, at least in the last 800,000 years and probably longer. And the question is, what path are we going to follow? Okay, so we have this business as usual path, which will take us way up to the top there at our current emissions rates. And we could have something that the sort of current commitment, which a lot of people refer to as 1.5 or 2 degrees, but it's really, in reality, we've only agreed to about 3.5 degrees at this stage. And if we ratchet things down, we can take our emissions down there, okay? And the question is, so which track do we follow? Which path do we follow? So in the models, what we usually do is a sort of a business as usual path, and we'll do a mitigation scenario, and then we'll compare the two. So what are the benefits of mitigating climate change? That's a very important question to ask. Okay. And so to answer that question is we have these models, okay, and these are the historical observations there with uncertainty around them. And we have our range of possible outcomes in terms of global temperature. There's a lot of uncertainty there. Okay, that spread, our spread is a range of possible futures. Okay, but that spread is really largely determined about the path we take. So if we continue on a business as usual path, we're looking at about 3 to 5 degrees of warming. Okay, and you can think of that's globally, that includes the ocean. So if we think about land, that might be about double over land or so. And if you think of a world with, say, 6, 8, 10 degrees warmer, that's it's a completely different planet that we would live in, and there are very severe consequences to that. And a mitigation path maybe would be 1 to 3 degrees warming, which is still substantial, but obviously much lower or much better than the business as usual path. And I'll just summarize the current knowledge. It's warming. It's us. It's a very simple thermodynamic process. Climate change is not rocket science. It's very simple. It's basic thermodynamics has been known about for hundreds of years, and our Earth requires these greenhouse gases. We need greenhouse gases. It's the addition of additional greenhouse gases that are posing the problem. Our ice is shrinking, as you see in the picture there. Sea level is rising. CO2 in the atmosphere, carbon dioxide in the atmosphere is up 40% since the 1800s, and it's at its highest in at least 800,000 years. I'm getting a lot of feedback from the microphone. Cumulative emissions set the emissions. So you can see that we've done most of our emissions since 1950, and that's when we're seeing most of our warming. So those cumulative emissions there, once they go up there, they stay up there for a long time. Our carbon dioxide is up there for about 100 years or so, as well as our nitrous oxide, and the methane is up there for a shorter time. But the global warming potentials of these gases are very high, of the nitrous oxide and methane. Without mitigations, concentrations are expected to more than triple, and 2100 temperatures are projected to increase by 1 to 5 degrees, depending largely on our emissions pathway. Warming is greater over land. It's very important to understand that. So when somebody says 4 degrees of warming, we have to think about that as closer to double that over land. So that's very big. Those are very large differences. The warming will last for centuries. So once those, like I mentioned earlier, the emissions are cumulative, and the greenhouse gases remain in the atmosphere for quite a long time. And the short-term impacts, unfortunately, tend to be largely negative. Okay, so the impacts of climate change on our various sectors. And so that's the question. So I guess so people talk about 4 degrees warming. What does that really mean? Okay, and so we want to look at, we have various sectors that could impact. So we have warmer temperatures. Precipitation changes, so maybe wetter regions getting wetter, drier regions getting drier, and sea level rise. Okay, so and what impacts do those have on our various sectors? I'll focus here on the human health impacts and looking at heat stress, okay, and then the water resources impacts. So this comes from a fairly recent paper from by myself and Professor Elta here at MIT, and we focused actually on this region here. And the funding actually came from was partially funded by the Kuwait Foundation for the Advancement of Science. Okay, so traditionally we speak of heat. When we speak of heat waves, we think of just temperature. The weather forecast will tell us it's temperature, but that doesn't really give us a good measure of what a heat wave is. And in fact, some of the weather services provide what's called like a feels-like temperature or a heat index or something like that, and that accounts for humidity. Okay, those variables that they give you aren't really physically relevant, but we have another variable that we call wet bulb temperature, which is often used by meteorological services. It's a very important thermodynamic variable, and it's a very good measure of there's a physical meaning to this. Okay, dry bulb temperature, so I'll refer to it here as dry bulb temperature, but this is a temperature that we normally think of. If you say it's 20 degrees today, that's the dry bulb temperature. It's just the current air temperature in the shade. Okay, the variable that I want to introduce is called wet bulb temperature, and it's a temperature to which air would cool if water were evaporated into it until saturation at constant pressure. So if you imagine this room, okay, and I start injecting water vapor just with the misters, which you probably have here in restaurants, you inject the misters in here. At some point, the temperature will cool, and at some point you'll reach saturation. That temperature you reach is called the wet bulb temperature. So if you have very hot and dry conditions, the air can take on a lot of moisture, and so the wet bulb temperature goes down, 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 right? If we have hot and humid conditions, the air can't take on much of the moisture. And so that's why these misters, which we see, I'm guessing you have these in restaurants here and other places, those misters work real well in arid desert climates, because the wet bulb temperatures are much lower. Okay. It's a combined measure of temperature and humidity. So the higher the wet bulb temperature, which is always lower than the dry bulb temperature, but the higher the wet bulb temperature, the higher the combined effects of temperature and humidity, and the higher the level of mugginess or discomfort. So the human body has basically 4 different mechanisms for cooling itself. Conduction, so if I touch a cold surface or a hot surface, the heat will transfer in and out. Okay, so the cold surface will then cool me. I have perspiration, which or sweat, convection, the transfer of heat from the body to the air, and also radiation, just being a body. My body is emitting heat. Okay, and in hot conditions in all conditions, our core temperature is about 37 degrees Celsius. Okay, and our body aims to maintain that 37 degrees. But the skin temperature in hot conditions is maintained at a colder temperature. So we have 37 to 35 degrees. That gradient allows us to shed heat from the body. Okay. Now, at some point when the temperatures get so hot, let's say it's very hot outside, all the mechanisms shut down except for the perspiration mechanism. Okay, so it'll get so hot out that we can't cool with the other mechanisms very efficiently. And the last one remaining is our sort of perspiration. And if the wet bulb temperature exceeds 35 degrees, heat can no longer be dissipated from the body, and within 6 hours, a healthy human being will perish under those conditions. So this number, which sounds kind of low, 35 degrees, is a low number, but in wet bulb temperature terms, it's a very high number. In fact, if we look at the U.S. National Weather Service heat index, that's about 77 degrees Celsius, which is a very, very high number. And the question is really, do we see that in nature? And just to mention, talking about this sort of feels like temperature or heat index, extreme danger threshold is around a wet bulb temperature of 29 degrees. Okay, so we are in extreme danger conditions. So the weaker of us would be in very extreme danger at 29 or 30 degrees Celsius. Okay. So where do we see high wet bulb temperatures? So we did the analysis. We looked at the maximum wet bulb temperatures ever sort of measured. since from 1979 till 2015 in this case. And we see there's a few hot spot zones out here, and one of them happens to be in the Arabian Gulf here, the Gulf region. We also see some in the Southern Asia and the Red Sea, and a bit also even in parts of Baja California there and the Gulf of Mexico. So the region that stands out the most, so if we zoom in, is the Arabian Gulf region, and that's the sort of motivation of the study. So the question is, and if you look at the numbers, by the way, we're looking at, say, 30 degrees or so of our highest temperature. So in nature, wet bulb temperature rarely exceeds 30 degrees. And that's right around that extreme danger threshold there, okay? The Red Sea, Arabian Gulf, Indus, and Ganges valleys are very vulnerable to high wet temperatures of exceeding 29 degrees, and we'll show some results in that in a second. And so the question is, do we have the potential of exceeding that 35-degree threshold? That threshold for human survivability is the reality. Okay, will certain regions become uninhabitable at certain times of the year? The formatting. So we designed a set of numerical experiments there, and I apologize, the formatting seems to have gotten awry in the transfer to the computer. But we had 3 global climate models, so those big models I showed earlier, okay, with 3 different sort of simulations. One is a present day, or a historical simulation, we call it. It's from 1976 to 2005, 30-year simulation. And we call that the historical, or sort of we're trying to reproduce the previous climate. And 2 future scenarios. One is the business as usual scenario, and then one with a fairly substantial mitigation. And then we have a high-resolution climate model. It's the MIT regional climate model that we specifically customized for the region. We included dust processes when we have the dust storms here, so that's a very important factor of climate. And we modified the land surface to better represent the sort of desert conditions of the region, as well as a few other factors, including how air mixes and things like that. And these were performed at Singapore, in a center at Singapore and MIT. That's the domain we used. And then through those experiments, or high-resolution experiments, 25-kilometer by 25-kilometer grid, so we zoomed into the region using this regional climate model at high resolution, and we can say something about the regional impacts on heat waves. If you notice these global models, we don't directly use them because they're at a very coarse grid. They're around 200 kilometers by 200 kilometers. We zoom in at a 25-kilometer resolution there. Okay, so here are some of the results. This is the historical simulation of wet bulb temperature. We can think of that as heat stress. And remember, we're looking for that 35-degree maximum temperature, but we can also look for 30-degree regions as well. So that extreme danger threshold, and this is the survivability threshold there, okay, human survivability. And we can see in our historical climate, there are some regions of extreme danger. However, wet bulb temperature does not exceed the 35-degree threshold, okay, or even come close. Okay. If we go into our business as usual scenario, that RCP 8.5, okay, our business as usual scenario, we can see that much of the Gulf region, you can also see the Red Sea, there are regions where we actually now hit that 35-degree threshold, okay, this threshold for human survivability. If you look closely at Kuwait, actually Kuwait is very isolated from that, and it's largely due to the Shamal winds, I believe they're called, that come from the northeast and Iraq into the region. This dry air that protects you from keeps the humidity from going up. But other regions, if you look at, say, the Emirates and Qatar and other places, you can see that they're much more, the wet bulb temperatures actually exceed that survivability threshold. With mitigation, which is interesting, and I'll show more plots of this in a second, but with mitigation, we don't see any hits of the 35-degree threshold over the land regions. Yeah. So the region really stands to benefit from climate change measures. I'll put it back. Okay. Oops, okay, go ahead. Okay. And just to look at dry bulb temperature, okay, again, this is our regular air temperature. This is just the maximum value in the 30 years of simulation. And we can look here at our basic values here in we can see, values up to around 50-something degrees. In fact, I think Kuwait hit 54 degrees the summer before last. And we can look at our business as usual scenario, and we can see now we have regions well above 60 degrees here. If we look in this purple region, we have 60-degree weather, certain events that could potentially occur in a 30-year span. Okay, I'm not saying this would happen every summer, but it could potentially occur in a 30-year span or so, or even more frequently. Okay, and we'll come back to this plot later on. I'll show you maps of a recent a heat wave event that you had a year and a half ago in the region. Okay. With mitigation, obviously these temperatures significantly reduce. Okay, so again, the benefits of mitigating climate change. Okay, these are a time series for different sort of important cities in the region, and if you can see, it goes from basically 1975 to 2100, and the blue lines are the historical simulations for wet bulb temperature. And then the three simulations, that's why there are three lines, and it gives us a measure of the sort of variability we can get. And then we have our future simulations, where the green is our mitigation scenario, and the red is our business as usual scenario. And so probably the first place you're looking is Kuwait, and you say, well, we don't get up to that 35-degree threshold, and we'll come back to this and look at this more closely. That's a good thing. But however, you look at your neighbors, say in Doha, we actually have an exceedance of Abu Dhabi and Dubai. There are exceedances of this 35-degree threshold. So if climate change remains unabated, these regions can really, at certain times, certain years, they may very much suffer the consequences of climate change in their human populations there. If you notice also with the green lines, none of the green lines exceed that 35-degree threshold there. Okay, so again, the benefits of mitigating climate change. Another note is the 29-degree events, so that extreme weather, that extreme danger threshold, they're projected to be exceeded in most summers, regardless of the mitigation scenario. So if you just take any Dahran, you can take the 29-degree threshold, and you see that is exceeded. The extreme danger it would occur very likely every summer. Yeah. So I zoomed in on this plot just for Kuwait here, and we can see the shades here. This is a danger region. So if we're in the yellow region here, we're in we can have a danger condition every year that the line is in this yellow area means that we've had danger or potential danger to human health, and extreme danger if we're into this red or pinkish area there, okay? And you can see that while Kuwait never approaches the survivability limit, which is a very good thing, there are these sort of severe danger conditions where the body cannot, where heat stress conditions occur nearly every summer if we go as business as usual. Another I just focus on, which for obvious reasons, is Mecca, and if we think of the pilgrims that go there every year, and when the Hajj, and with the lunar calendar, if it coincides with as it is right now with these summer months, there are severe risks to human health there. And you can see, so there have been events that have caused, resulted in stampedes. So they don't really know the exact reasons for the stampedes, but those stampedes with people dying actually occurred when there were very severe hot conditions in the region. And you can see with the future climate that would be in extreme danger conditions potentially during, depending on when the Hajj fell with the lunar calendar, could be potentially dangerous for the pilgrims. We can also look at the statistics a little bit more, and these are histograms here, and we see the numbers here, which you probably can't see, but this is the 50%. This is the number that this is sort of the 50th percentile, so it's the median value, and so it's sort of the typical summer day. Okay, so half the events in a summer, say in Kuwait, the wet bulb temperature would be about 20 degrees on half of the days. Half the days it would be below 20 degrees, half the days above 20 degrees. We also have the 95th percentile, which would be about the warmest week of the summer in terms of the heat stress, which would be about 25 degrees or so. So you could in the present climate. And if we go, and I'll zoom in on that in a bit, but the take-home points of this are the highest generally in most of the regions, the highest heat stress week is projected to be a normal summer day in most cities. So the current, sort of the worst week that we have of the summer is projected to become a normal day in the future under the business as usual scenario. Okay. In many Gulf cities, events exceeding that sort of 29-degree extreme danger threshold are projected to occur on average several days every summer. Okay. And again, zooming into the Kuwait region so we can see the numbers a little better here. And we can see that the 25 degrees, for example, is the current worst week in Kuwait, is closer. It's not, actually the region does quite well in terms of its wet bulb temperature, but it becomes 22 degrees in the future scenario. Looking at Mecca, similar. So we can just see here that the fact that these tails are shifted over into the extreme danger zone, okay, in both of these cases here. Okay, so when this hit the press, there was a lot of attention from this work, and it just so happened right when the article came out that on July 31st in 2015 in Bandar Mashar, so there's a couple regions in Iran along the Gulf there that are very sensitive, and we just approached, this is actually from a meteorological station, they just barely missed the 35-degree threshold there, just for a very short instance in their weather. Okay. If we look at maximum dry bulb temperatures, so again, I mentioned that you're not as vulnerable to the heat stress here in Kuwait, but the dry bulb temperature, the regular air temperature, are quite vulnerable. And you can see here, these are from it's actually weather that occurred on July 22nd, 2016. And this green area here is our temperatures. The temperatures actually reach 54 degrees in those regions there. I'm sure some of you remember that. And you can see, if you look at this map and compare it to the previous one that I showed, this looks very similar, okay? The patterns there look extremely similar. So that event, how the temperatures are increasing match very, very well with what we project in the model. And I don't need to tell you this, being where we are today, but much of the coasts of the Gulf are inhabited, as well as the Red Sea, and populations are growing. We know that this is one of the fastest growing populations are growing, some of the fastest, much higher than the global average in the region. And so these are important considerations when, obviously, in the development of the region. So what are the mechanisms for this? This is a question that we had to answer in the study. Why is this region vulnerable to these heat stress conditions? And it's really due to the presence of the Arabian Gulf. Okay, it's a very shallow water body. Okay, so these red lines are 20-meter, the bathymetry at 20 meters, and then 50 meters. Okay, so most of the Red Sea is let's just say on average around 50 meters. It's very shallow. Okay, we have very high temperatures in the summertime. These are the sea surface temperatures are greater than 31 degrees, which is extremely warm. And those two factors, coupled with it's a largely cloud-free region, the presence of the Himalayas, we have the air descending on the region. So even if you have this moisture, this very moist air, it can't lift up and form clouds. So it stays down there. The temperatures and the humidities get very high over the Gulf. Okay, so it's a very shallow, hot swimming pool. So you have, again, subsidence region, okay, clouds can't really form, and you have the high temperatures of a land, so combined high humidity. Shallow warm waters, they provide moisture, or moisture source, okay, high temperatures and moisture, you have very hot and humid conditions. And the evaporation, by the way, is about 2 meters per year, which is quite high for oceans. And combining all that, we have the potential for very high wet bulb temperatures and heat stress. Similar mechanisms in place for the Red Sea, and when you could look at Mecca or something. Kuwait, so I mentioned already, but it's protected largely by the summer winds that you're all familiar with. I apologize for the Shamal winds that you have. So. these are the mechanisms. I won't go through, I just kind of basically went through them, but we addressed these with a series of additional simulations we actually performed a simulation with the Gulf and a simulation without the Gulf and looked at the differences between the two. And we were able to identify exactly how these mechanisms came into play. Okay, so let's shift over to water resources in California. Okay, California is really the largest, world's largest, most productive, and actually most controversial water system. Yeah. And I hope my conversions were correct to metric units, but we have about 49 cubic kilometers per year of water that we're moving around, and 30 million people, and 2.3 million hectares of irrigation. So it's a very, the agriculture in the region is very extremely productive. It's one of the most productive regions in the world for agriculture. And but these basins here, which I've highlighted here, these river watersheds or river basins, a lot of them, they supply water just to Southern California. Yeah, we have, as I said, about 30 million people, and we're importing the water from outside the region. We do have some local supplies. About 20% of our water is local. Okay, so we have some groundwater. We count recycled water now as local supply. I think you have a few percent here of recycled water. And conservation is actually considered a local supply as well. So if we move down from our baseline, that's considered local water. But we get about 20% of our water from outside of the basin, from within the basin, and 80% comes from outside. And the three basins are the original, the Los Angeles Aqueduct, or the Mono Lake Owens Valley Basin here, this sort of red color. And we have the Colorado River Aqueduct, which looks very large in terms of its area, but most of this region is very arid, so most of the water is coming from the Rocky Mountains. And in this area, there's not much water being generated in the region, and we basically take water, pump it, series of pumping stations, pipe it, and through aqueducts, bring it to the Southern California region. And the last one is what we call the State Water Project, or California Aqueduct, which brings water in from the Sacramento River and the San Joaquin River from San Francisco, and then we put it through aqueducts and a piping system and bring it down into Los Angeles and irrigate the Central Valley along the way. So there's massive amounts of water being transferred around. You can see that these are all our aqueducts here, basically moving water around the basin. We're bringing it in from different regions. And we've also experienced severe drought recently, and now we have a very good year in terms of water. This is, again, that satellite I showed about measuring land mass. Now we have, it can also measure groundwater changes, groundwater levels, and we can see that our groundwater levels have been decreasing quite a bit, so a lot of our water does come from the ground. It's a great source of water. It's able to be stored down there cheaply. And you can see it, say, for example, Folsom Lake, which is one of our water supply reservoirs. We have two different dates here. This is 2011 and 2014, just in 3 years, our reservoir is dried there. And now it's back up again. So. It's very important, and I think you can fully appreciate this here in Kuwait, but water and energy, there's a nexus between the two, okay? Especially with desalination. Desalination, is, at least in the United States, is very expensive. It's about twice the cost of us moving water all over the state. And in California, 19% of our energy, our electricity, goes to moving water around and treating water. Okay, I imagine the number might even be higher here in Kuwait. Our hydrologic cycle is very similar to yours. Okay, and I guess if you think, well, you get your precipitation in the wintertime. We use what's called a water year. We don't use a calendar year for our water. We start October 1st and go to September 30th. And you get most of your rain, I understand, in the wintertime, and as do we. And I think if we think of the Tigris and Euphrates rivers that's coming, the winter precipitation, which falls with snow in the mountains there, it forms in the wintertime. Okay, snow melt. Okay, so when we're getting our water is shifted, our runoff is shifted towards later in the season, and simply due to snowmelt processes. So these snowpack provides a large source of water storage for us. It's a natural, very cheap source of water, storing of water. Okay, and our demands tend to be highest in the summer for obvious reasons. 75% of of our stream flow is from snow melt, okay, which obviously you don't get that here unless you have some sources from the Tigris and Euphrates. We have water, so we have all those lots of reservoirs, just hundreds of reservoirs in our system that we can store. We store our water back, or hold our water back to for use in the summertime when demands are highest. We also have very large water reservoirs in our system. Maybe you've seen Lake Mead or something, and those will get us through very long droughts, multi-year droughts, and those are the reservoirs that saved us in our last drought. Okay? And what's really important to understand, at least in our system, is that our reservoirs are used, our primary use of the reservoirs is flood control. So in the wintertime, when we're getting our rain or precipitation, we actually lower the water levels of our reservoirs. Okay? But luckily, we have the snowpack in the mountains to be a natural source, or a natural reservoir for us. Okay? So a lot of the winter precipitation we get, if it falls as rainfall, we have to just let it through the system and go out into the oceans. Okay? So I think if you can imagine that with our snowpack, our dependence on the snowpack, that our system may be vulnerable to a warming climate. Okay? In this case, we did a series of simulations and 10 global climate models, and we zoomed in at 16 kilometers with the regional model like we did before. And we then went even down to 4 kilometers using a hydrologic model, and then finally we were able to assess its impacts on water resources. We used this was more for our policymakers, so we did a short-term future, so we didn't go to 2100, we stopped at 2050. So we're really looking at the next 30 years or so, and how to adapt to the changes that we could expect at a sort of a policy or decision-making timescale. And they were performed on Oak Ridge National Labs Titan, which at the time was the fastest supercomputer in the world. And I just mentioned they released Summit, which is now the fastest again. It's currently the 7th fastest now. And it's also still, at this time, the most comprehensive set of simulations that are available for the United States. Go ahead. Okay. Again, this was done, like I said, on Titan. And again, this looks like a computer chip, but this is actually 2 meters there in height of just computers all over the place. Okay. Basically racks of computers. So we look at our changes. So all these plots are going to be differences. So the future, the near future minus the historical simulation. And we can see our temperature changes. We see that which you probably are not aware with the orography of the region, but these temperature changes are most sensitive in the higher elevation regions. Again, that's largely due to what's called the snow albedo effect. So if we change from our land from snow to, say, soil or vegetation, it will absorb more energy, and then that will melt more snow, which will then absorb more energy, and so on. It's actually called a positive feedback. Okay? And so we see that those higher elevations are very sensitive, and we're looking at around just by the end of the century, and this should say 1 to 2 degrees Celsius increase. Okay, that's Fahrenheit. About 1 to 2 degrees of warming just in the next 30 years. And looking at snow depth, again, these are our high elevation regions, and we see up to a 75% decrease in our snowpack. Okay. Precipitation. So our region actually happens to benefit from, I guess, from the precipitation side of things. So I think if you can imagine, a warmer temperature would cause more evaporation, which then causes the potential for higher amounts of precipitation. We see several percent increase in precipitation over these basins, and if this is just showing seasonality. One of the problems with this, though, we have the extra precipitation. However, this plot is showing that most of the precipitation is going to increase in the winter. We're not going to get it in different seasons, which would be the hope there. So in some sense, that water is going to be wasted because our reservoirs are in flood control mode, so we have to release all that extra water that we would get with the higher precipitation. Evapotranspiration, you can imagine with a higher climate, we expect our, say, irrigation demands to go up with with climate, with higher temperatures. And also, if we have any surface reservoirs or aqueducts, the evaporative losses from those systems would increase. So this is one of the key plots here. This is mid-flow date. This is the date at which half of the runoff comes to us, and the other, so it's sort of a median in some sense. So the date at which half of the runoff for that water year has arrived in our system, and the other half will come later. And this is using well, basically the take-home point here is that just within the next 30 years, we would expect our runoff to arrive about 10 days earlier, which doesn't sound like a lot, but it is fairly significant. And so this is essentially saying that this part of the year, so we have December, January, February, March, April, May, that part of the year will become wetter, more of our runoff will shift towards earlier times of the year, and then we'll have less available to us in the summertime. Okay. So we have more precipitation falling as rainfall, okay? So we don't have it coming as snow anymore, and then the snow is also melting earlier, so we have less of that natural storage in our system that I was talking about, which poses problems for our artificial storage and flooding issues. Okay. And again, just to re-emphasize that our winter water levels are maintained at a low level for our flood control, okay, to protect our societies. Okay, so it's really in conflict with our storage needs there. And the question is how to adapt to that. Also looking at just wet years and dry years. Okay, this is like a 50-year event where we looked at all the different return periods, but the event that's on average would occur every 50 years, our wettest event, a 50-year event. And you can see that in most of the basins here that we talked about, where we see lots of blue there, but the wet periods will increase in the future. So we have these lots of more wet years. So the 50-year event might become as frequent as, say, 15 years or so, or 25 or 40 years in the other basins. So they become more frequent. And if we look at dry years, okay, the same thing, but for dry years, and we can see that in most of the basins, we're also seeing a bit of an increase in the dry years as well. So those sort of drought years versus the wet years. So in some sense, what we're seeing is less normal years. Okay, so a flip-flop between the wet years and the dry years. That, for anybody who does water resources, is a big problem, because we just want to know if it's the same every year. It's very easy to plan for that, but if we don't know what's going to happen, it's very hard to plan for those situations. So the reliability is a big issue there. And if we look at flood events, so these are just some flood event that could happen. And what we see here is that all this blue means that the flood events are projected to become more frequent just in the next 30 years. So the 50-year event might be as frequent as, say, every 20 years or so. Okay. And that causes, this is our basins, largely urbanized here, our Southern California regions, and that poses problems for us. So we have more flooding. We might actually have to lower the reservoirs even more. So if we're expecting more flooding to come, the flood control levels, those rule curves for our reservoirs, have to go a little bit lower, which causes problems for our storage again. Okay. And then we also have issues with our flood control systems. We've channelized most of our urban settings to move the water out of our system as fast as possible. Those have a certain capacity. If we're going to have larger events, we might have to retrofit those systems. So this is just a summary of our future water cycle. That original curve the curves I showed before of our hydrologic cycle of the region, and we also have our snowpack. But we have substantial reductions in snowfall and snowpack, so our snow line is essentially moving up. Earlier snow melt, so we have a shift of the green curve towards earlier in the year. Okay. And we also have it being higher. We have these rainfall events. We don't have the snow storage anymore, so it's coming in as rainfall or liquid and goes directly into our system. In fact, there's an increased rain flood risk. We can even have rain falling on top of snow, which is even more problematic. And there's a substantial increase in extreme frequency, storm frequency and intensity. Higher irrigation demands, so that demand curve goes up. That's not accounting for population growth, but you could expect, if you include that there, would even go higher. And higher evaporative losses from our reservoirs. Okay, so we're losing water just from the warmer temperatures, and increased So if we look at these differences here, we see an increase in deficit of our system. So I like to think of this as our 20th century infrastructure in California is not equipped to handle a 21st century climate. And so there's various measures that are being looked at to make our system more resilient to climate change. And just to go through these, okay, so we haven't mentioned population, but this is very important in your region, obviously, but our population is increasing quite a bit, less than yours, but we're expecting about a 25% increase by 2050. These are our California and our Southern California increases there. And so we also have to account for these growing populations with our changing demands. So in our baseline demand, we use actually somewhere around 500 liters per capita per person per day, okay? And I looked up online, I don't know how valid the source is, but it's about the same as Kuwait, okay? So we use about the same water per day, which is surprising because I see it's very urbanized here. A lot of our water goes to irrigating our gardens and yards and things. So the issues are that we can't really conserve our way out of this system, because if we just use less water, which is very possible, many countries use a lot less water than we do in Southern California, but with our population increases, we're not able to conserve our way out of that, at least at the way people look at it. We have a lot of outdoor irrigation, and I know that you have some here, but not as extensive as we do, but you can just see this is our agriculture, and these are we have golf courses in the middle of the desert, which you probably have some in some of the countries here. So urban and agriculture irrigation demands are expected to increase with our increasing population, but also just with climate change. It's going to take more water to keep these areas green in the future if we go on the business as usual scenario. At current, we need about 1.3 meters of water to maintain our grassland, our turf, our grass lawns. And that, as I said, that will increase. And we're fortunate we would get a little bit more precipitation. So some of that could be offset, but the problem is that precipitation for us comes in the wintertime, and our plants aren't transpiring as much as they need it in the summer, but the precipitation is coming in the winter. Yeah. We did a study for actually one of the cities, the water departments, and they wanted to know how useful rain barrels are. These are basically, let's call it 200 liter barrels that just capture water from your rooftops. Again, the issue is timing, okay? So you get the water in the winter when your yards don't need the water. And it didn't actually show, the study showed that it wasn't very useful to do that. They wanted to provide incentives for their customers to use those. What has been effective, though, is we have called turf rebate programs. We pay people, so a lot of people have a garden or a yard in front of their homes, and the water companies are paying people to remove those and put in low water use plants. And so those are proved to be very effective. They're cheaper than the actual cost of water. And I think one of the big issues is our agriculture. It's our largest water. About 80% of our water is agricultural water that we're talking about in our system, and the water is essentially subsidized, so there's no incentive for them to conserve the water as much. So we have to come up with ways to have them conserve water more in the agricultural sector. This could be, and I don't know if this is being done in Kuwait, but stormwater capture, spreading grounds to recharge your groundwater systems here. This is done in Los Angeles. We have spreading grounds where we bring water. Some of it is just rainwater, but we also bring treated water. So our advanced treated water or recycled water we put in there. We can store imported water in the ground and storm water. So those three factors to replenish our aquifers and store water very cheaply. It's a lot cheaper than building a reservoir. And the nice thing about this system is that the recycled water, it allows the ecosystem to essentially do an extra sort of run through of the treatment of the water. The problem is most of our area is urbanized, so we don't have many areas for spreading grounds. I don't think that's as much of a problem here. And so when we have extra water coming through our system, we can then try to store it. So it's a good alternative to raising our reservoirs. So one of the alternatives is actually to raise our reservoirs, which I think I'll show in a second. increased groundwater banking, so this is what I just mentioned, and the issue is we need more infrastructure to store waters off stream in groundwater banks. So I think in my opinion, one of the best places to store water is in the ground. Okay, it's much cheaper. We've depleted our aquifers so we can replenish them, and it's much cheaper than building a reservoir. Recycled water. It generates, we're at about a half a cubic kilometer a year. It's about, in Los Angeles, is 2% of our supply. We're not allowed to drink the water, okay? But it needs to be a bigger part of our solution. We have a potentially doubling, we could even do more than that by 2035, but our current laws don't allow us to drink the water directly, even though it's at a quality where we could in many cases. Not all of it is, but we could drink it. It's really, they call it toilet to tap, the sort of negative perception of drinking recycled water is something that we need to get over, I think. Even though water's been recycled through its system many, many times, if you think about it. It's not as valued as much as potable water, so we actually sell it for irrigation of our golf courses and other places, so it has a lower value. In our campus, actually uses it for its irrigation as well. And you can use it in cooling towers as well, so which I think you do here, I believe, or at least you're. Infrastructure, we have a project that's on the ballot to basically, we have issues with endangered species there that get confused with us reversing the water around in the flows. It's called a delta smelt. It's an indicator species. It's a sort of a species that's very important for the full cycle of the ecosystems. And they're talking about putting a tunnel underneath our delta this is the San Francisco Bay here, putting a tunnel underneath that to keep the fish from getting confused. The idea is to improve resilience in our system. We could also raise our surface storage. Okay, so in some cases we don't have many more sites for building reservoirs anymore that are good places for it, but we can potentially raise our reservoirs up to increase the flood control capacity. And we could do infrastructural improvements, also even covering. So I don't know if you may have seen these balls that they put on our reservoirs now to reduce evaporation. So, and there's even now just talk, I just saw it in the news, where they put solar panels on top of a reservoir. So they generate electricity at the same time reducing the evaporation losses. Stormwater capture, already mentioned, recharge of groundwater banking, and our 2 tunnels, it's now maybe perhaps a 1-tunnel project. There's talk about that. Our management strategies, it won't go through this curve too much, but we can, when all these rules were put in our reservoirs, it was before we had very good weather forecasting. We didn't have our meteorological services to give us our projected, what rain might be in 5 days from now or something. And so usually when we have some rain event coming in, that water just gets, in the wintertime, that water can get wasted and we have to drop the reservoir levels down. But now if we know, if we have a lead time of 5 days or even less, we can decide whether we'll release the water or not. Okay, we can even store it back for hydropower or something like that. Okay. Another thing that we're doing is it's called ag to urban transfers. We're paying farmers not to farm now, so that's it's a source of water supply for us. As well as mainly done in San Diego, but they pay farmers in the Imperial Valley not to farm there, and so that they can get their water rights. Okay, so that's a summary of the presentation. Again, thank the Supreme Council for Planning and Development and also the UNDP for allowing me to speak today. Okay.
Thank you, Professor Jeremy, for a very educative lecture on 2 key issues, climate change and water issues. As per the latest report on UNESCO, the future wars are going to be wars of water. And I think you've done a fantastic job breaking down at an individual level 2 key issues that we face as we progress through the future. We'll open the floor to questions and answers. Please state your name and your question and the entity you work for.
Yes.
Go ahead.
Do I need a microphone? Yeah. My name is Mohammed Al-Shawaf, assistant professor in Kuwait University. I have some modeling questions. I hope you don't mind.
Of course not. My
I'm not a
area of
climate
expertise.
expert, but I deal with other types of models. I have a question about the inputs of the model. Where do you gather the data? Are they individual data points on the globe, or are they geospatial, remote sensing images that go into the model? If you can briefly talk about, and also the outputs. I see this graph of increasing temperatures. I know they're average, but is there a way to see the spread of, data around the
Yeah,
average? Thank
so
you.
those are very important questions. And first of all, the models are essentially generating their own data. So you need just a few, the input variables are essentially the solar constant. Okay, so 1,366 watts per meter squared is the energy that arrives to Earth's surface. And then that energy then gets distributed around the globe. Another you need is the greenhouse gases, because those will trap our heat in. So, and so even in the natural system, we need the greenhouse gases. And we need the land cover data. So it depends on how detailed the model is. Some models will fix the vegetation. So if there's a forest, desert, grassland, and so on. And other models will actually simulate the progression of the changes in vegetation through time. So if we go to a drier climate, maybe a forest would shift into a grassland or something. And the rest of it is essentially simulated by itself. So you need, obviously need the topography and the bathymetry of the oceans, but all of that is generated by itself. And if you take the regional models, what the regional models do is you zoom into a region of focus. So the idea is that it's just like the rest of the pixels on your camera, and you can zoom in a particular region, and you feed in the information from the boundaries of the model. And but basically, the process is the same. The comparison data sets that we use, so when we verify the models, come from a variety of sources. It can be in situ observational data, say from the Met Services. It can be from the Met Service in the United Kingdom. They have the ECMWF, which is the European Center for Medium Range Weather Forecasts. They provide a lot of very good data that assimilate data from different sources, from satellites, from stations, from actually models. They'll fill in gaps with models and things like that. So that's sort of our best global data set available. And then we have the meteorological data. Does that answer your first question?
Yes.
Okay,
Yes,
and the second question, just
the graphs showing the temperature increases, and these are global averages.
Yeah.
And I was wondering if the spread around the data is something. I mean,
Okay, so
I've never seen the spread before.
Okay, so the spread you're asking about on the observations or on the models?
Observations.
Observations.
Yes.
The spread, there are data. In fact, one of the plots did have see if I can get to it here. Well, it did have the spread on it. You can see the uncertainty there. See, unfortunately with animations, it goes a little slower. I should have just escaped out, but. You can see in the, this shows some range of the uncertainty there, that sort of gray area there. And you can see the uncertainty was much greater, obviously, when there were less observations. And that uncertainty range has decreased. But if the question is our warming outside of that uncertainty, there's no question about that. So there's no question if you look at the statistics in whatever measure you want to use. But I don't know the exact p-value of it. It's not my area. But it's well out of that range of uncertainty that we've seen in the last 50 years or so.
Thank you.
Next question, gentleman on the front row.
Assalamu alaikum. Thank you very much for the presentation. I'm Dr. Mohammed Al Saidan. I'm from the Ministry of Health. I'm also the head of the Environmental Health Department. These talks about climate change are very important. We think it's extremely important to have this awareness, knowing the impacts and such that are related to climate change. But in most of these talks, there's always this focus on the hazards that are going to happen due to climate change, but there's very little focus on the other aspects, especially in countries like Kuwait. So for example, there are a lot of countries that are reliant on, the economies are reliant on fossil fuels, and usually they are low in resources, or natural resources, human capital and such. And from the health perspective, if you have these countries shift from that kind of economy, or shift from that kind of fossil fuel-based economy, this might cause like some regression in the advancement of health, advances that happen because of improved spending on the health services and such. And I think it'll be helpful if these presentations in the future, especially in countries like Kuwait, would have a more integrated approach that covers both the health impacts of climate change and the economic impact, and probably some sort of like solution or some sort of help to guide these countries in the right direction to help find solutions for climate change, but at the same time not regress in the sense of the economy and sense of health and such. I don't know if you have any thoughts on that.
Yeah, I think the solutions haven't really necessarily been come up with yet, and I think it's unique for each region, each situation. I think it's a valid point, though, of course, and I intentionally leave out that because my area, it's not my area of expertise, so I don't want to step into the realm of say a social scientist or something like that. But I don't even think, at least from my perspective, I'm not saying to not burn fossil fuels. I think it's just, I'm saying to burn them cleanly. So, and cleanly would, so we've done made a lot of advances in reducing the emissions coming from tailpipes of our cars, from our power plants. And when we think of the sulfates or the smog coming from these sources, but we haven't done much in terms of the carbon dioxide. And the carbon dioxide and the greenhouse gases can be removed before burning or even after burning of the fossil fuels. So there may be measures in place that could allow Kuwait to burn its fossil fuels, but just do so in a cleaner way. And so obviously that requires more energy. So I don't know what exactly the amount of that is, but it could be a tax of 20, 30% or something like that, or perhaps even more. But that is a viable solution. Shifting to renewables is obviously a way to go here. You're in a region here where you could benefit from both the solar photovoltaics or even thermally generated energy, and as well as winds. I assume you could use wind turbines quite a bit here, so shifting into those technologies. But you probably, I think the solutions come from a lot of different angles, but I personally don't think, if you think of the consequences that climate could change could have on our societies, I think those are probably going to be more costly than to shifting to different, burning your energy cleanly or looking for renewables.
Thank you.
Hello. Thank you. As expected, your outlook was gloomy.
Your name and entity?
Marwan Salama. And it looks like it's going to become hotter, obviously, and slightly more rain, but at the wrong time. So one way to mitigate it, as you propose, or as you foresee, is to conserve and store more for a non-rainy day. Obviously, we in the Gulf are going to pay a higher price, not only in terms of heat, but also in less revenue and income. Nevertheless, an interesting study presented last year was covering the Sahara with windmills and solar cells, which would not only create some 80 terabytes of kilowatts of terabytes or terawatts of electricity, but also would change the Sahara climate and create more rainfall and vegetation, bring it back to what it was 8,000 years ago. Any feedback on this?
Yeah, I am familiar with the study. It was actually a former colleague of mine who did the study, or was the lead author on it. I think those results need to be tested more with with all these hypotheses that we form. They need to do multiple experiments. I think that it would be good to do another set of having a few additional simulations from different groups to verify that. But certainly the impacts of wind turbines and solar panels do have regional effects on climate. To the extent that they would make the Sahara wet again, like I said, I think we want some
Over a
verification
100-year
on it.
period.
Yeah. So, and I think I don't know if it's really in the cards to cover the whole Sahara with solar panels, because you have to transmit that electricity to different locations, and they probably,
The solar panels is to generate electricity. The other effect is the blackness.
Yeah.
Reduces the reflection of light, especially with the albedo effect of the Sahara.
Yeah.
So we could probably paint our desert black, get half the results.
You just make things hotter here. Turn them white in the summertime, I guess.
Samia Daij, formerly UNDP, currently consulting with the World Bank. I wanted to just make a point, quite a crucial point for the audience here, which is, so the Kuwait Environment Public Authority released the second communication on climate change, and they've identified sea level rise as a potential problem. And they've, in the report, they've even identified the geographic locations where they expect sea level rise according to the two scenarios. So even with RCP 4.5. However, if you look at the development planning for Kuwait, the fourth master plan for Kuwait, and whatever future projects anticipated, we are going ahead with business as usual. I don't understand, like, it's one government producing two different reports that contradict each other, and I don't see climate change yet being taken seriously within the policy dialogue in Kuwait, and I think these lectures are quite crucial, but I think maybe for the next step we should also look at the economics of climate change. We should look at the cost savings for the future. If you anticipate billions of dollars for a port that's going to be underwater in 40 years, is it viable for us to do that? So I think this is just a comment. I would love to hear from yourself about, in California. I mean, it's one of the leading states in terms of taking climate change seriously. How did they bridge that gap between sort of policymakers and scientists and so on? Thank you.
Yeah, I don't know if I can answer that question. They're very, very good points, and I think I don't know what makes Californians different, but we are, I guess, maybe living in a beautiful state. We're very close to nature. We like to appreciate the nature, and I guess when we feel that it's at risk, we are willing to do more to protect it. But why, in other states where they may have nature as beautiful as us, they aren't as willing to protect it? I'm not really sure. You know, you mentioned sea level rise, and that is a threat in California. It's much more of a threat on our eastern seaboard in the Gulf of Mexico, like Florida and places like that. But we are already implementing measures. I'm sort of semi-involved in a study, or students involved in looking at in beach restoration projects that will make the sea level rise, that are more resilient to sea level rise, allowing the beaches to essentially naturally increase their elevations with dunes and things. But yeah, I can't answer your question. I don't know what makes us different. Yeah.
Well, thanks very much for the. Sorry, I introduced myself. My name is Mike Wood. I used to work for the Ministry of Electricity and Water on energy issues, sustainable energy issues, but now retired. Thanks very much for the really impressive presentation. And you commented on the Gulf could benefit enormously from mitigating measures, but it's not within our power. I mean, the policies are against us, most strongly against mitigation in the world, and secondly, the potential is very, very small. The per capita values are huge, but the numbers are small, so this depends on the rest of the world. So now, if we're talking about the sustainability of the country, where the issue really is, have you looked at the progression for Kuwait, particularly in issues which affect sustainability? I've tried to get information in the past on this and found it very, very difficult. But I mean, the key issues are building cooling. Now, if the dry bulb temperature, the dry bulb and light bulb temperatures rise, then building cooling with air-cooled systems becomes more and more difficult. It drives you towards water-cooled systems, district cooling, which means major reorganization of developments. So that's one major issue. What sort of temperature rises are we talking about? You know, the scatter bands are huge, and Kuwait already specifies the highest dry bulb design temperature of any AC systems in the world. Unnecessarily, I believe, but that's what's happening. So it's good. They're going to go higher. It's going to become more and more difficult to design air-cooled air conditioning systems. The second issue is, so building efficiency is the number one thing. The next thing is renewable energy. We're way behind on renewable energy. We're talking about 15% of power, renewable power. We should be talking about 15% of energy. But the difficulty is that it's vulnerable to atmospheric turbidity. Now, what do you believe the effect of climate change is on turbidity in terms of atmospheric moisture and dust from desertification and adjacent areas and so on like that? Because these are the issues that are important to the sustainability of the country and the questions we have to answer.
Yeah, and I don't have the solutions for Kuwait, and I don't know how to answer all of the questions, but certainly putting wind turbines up does change the roughness of the surface, which then it tends to slow down the winds. But you know, our colleague over here mentioned the study in the Sahara, and that part of the effects of the wind turbines and the solar panels was to impact the microclimate, in this case a very large scale climate. But if you put the wind turbines up, you will slow down the winds, which would probably have a positive impact on dust, but it could impact your precipitation processes at a local scale. I don't know the direction that would impact them, but you know, those studies could easily be done though with these climate modeling systems. So one could say, okay, let's mimic a wind farm here at the scale of, say, something like Kuwait, and see what the impacts are on the microclimate of the region.
I think the concern is atmospheric turbidity. There's a big debate about what kind of solar power should be used, whether it's CSP or PV. Consensus seems to be PV is appropriate because it's less vulnerable to atmospheric turbidity than the CSP type. But the question is it going to get worse because of climate change? In the summer, there'll be obviously less moisture, but over the year, probably atmospheric turbidity could increase. So that's a question that has to be answered. The other point is talked about integrated water resource management in California and the business of the use of treated waste. Now that is a huge issue in Kuwait because we desperately short of groundwater, and at the moment we're using distillate for agriculture, we're using distillate for non-potable use. And so this business of shifting opinion into using treated waste, grey water and then ultimately black water is extremely important. And again, I wondered, in California, have you discriminated between grey water and black water in terms of use?
Gray water we're allowed to use in our home systems, so you can convert your garden to use gray water, but that water, we don't have a separate system for that. So you can do various measures in a commercial building as well, can dual pipe buildings and things like that, but we don't have any, our system, it mixes the two waters, the gray and the black water together, and then it treats them.
Well, it used to have separate systems, but it's not going anymore. Okay, thanks very much.
Well, thank you, Prof. Jeremy. Well, my name is, I'm Lieutenant Colonel Engineer Mohammed Hussein from the Kuwait National Guard. Well, in Kuwait National Guard, the KNG, we worked on several researches regarding water resources, like creating basins for the harvesting rainwater. So you talked about the pros and cons. Actually, you focused on the negativity of global warming. However, you didn't talk about the advantages regarding the rainwater and specifically in the rainwater. So we need to answer about this.
The rainwater in California or?
No, in Kuwait specifically.
And I didn't present any results on the changes in precipitation, and I don't recall offhand if it was projected to have more or less, but I believe you have about a third of the precipitation that we have in Southern California. So any increase in precipitation is probably beneficial to the region, especially if it can be captured. But I think that the amounts we're talking about, even if you double the precipitation here, it's still not going to be enough to meet the needs of the populations, I imagine. But I'd have to run the numbers on it. But so I don't know that in this particular region, you'd have to have massive changes in precipitation to have any enhanced benefit due to additional precipitation. But if you go there are other regions that could potentially, where these changes would result in a benefit, but I'm going to be, I guess, I'm a bit skeptical that it would have any real added value here.
Assalamu alaikum. Dr. Hassan Dashti, meteorology from Meteorology Department, Superintendent of Climatology. Thank you, Professor, for your excellent presentation. First of all, I think the slide which shows the extreme temperature for Kuwait, it was in 22nd of July 2016. I think, I'm not sure if the date is correct. It should be 21st of July. This is what we recorded in our database. And second, yeah. Of course, that was the record in the Asia, and now it's the highest during 76 years in the globe. So it was really extreme temperature recorded. Something else. What about as we know, in California, we have the most rain is in the north, and the people and the farms are in the south. So they face some floods. So how you manage the floods? Because as Sarah mentioned, that our second national communication shows that we have less rain in the future, but more intensity. So that's what caused the floods. So any solutions and studies regarding how to deal with the floods mechanism if you have in California? Thank you.
Thank you for the correction of the date. I'll update that. And then in terms of the floods, we are working on studies. There are various measures being put in place to infiltrate more water already. You identified exactly the issues that most of our rain comes from is in the north, but most of our population is in the south. And so it's about 75% of the water is in the north, and 75% of the population is in the south. So it's really the movement of water. We do have, I currently am involved in studies that are looking at how to manage our reservoirs better, as well as these infiltration mechanisms put in urban settings. But the nothing has been implemented at the reservoir scale yet. So things have only been implemented on the urban scales in our region. So nothing. We haven't done anything to figure out ways to store back more water. So we're currently just releasing any additional precipitation that comes through our system, or any rainfall that comes through our system during the winter time.
My name is Ali Muntasir. I'm from UNDP. I have two questions actually about the geographical coverage of the model. Does it cover all the planet, or there are areas that on the planet that you could not yet predict? And the second question is, if business as usual scenario continues, what are the least places that will going to be impacted by the global warming? Is there a prediction that we might move our agriculture to areas that has more rain so that we can sustain? Thank you.
So the first question about the model coverage, the models start at the global level, so they cover all portions of the globe. And then we zoom in a particular region. So we zoomed into sort of the Southwest Asia region. I think the domain extended up into beyond Turkey and then over into Europe and I don't remember exactly where the border cut off, but around, say, Afghanistan and down south into northern Africa and the Indian Ocean. And the second question, can you just repeat again? Yeah. Okay. So so there are adaptation strategies for agriculture, and so as part of a consultancy for the Nile Basin Initiative, and intro the Eastern Nile Technical Regional Office, and the idea was how to manage agriculture with these three nations: Sudan, Egypt, and Ethiopia. Involved is really the Eastern Nile, and so our strategies, what we came up with was to shift to different crops, okay, and to shift to different times of the year. They do have obviously storage on their system, so they have the ability to adapt to climate change and those strategies. But in Kuwait, I think you'd have to make agreements, and I don't know if you already have them at the regional level. So make agreements, say, with Turkey and Iraq and other places to share resources. And I don't know the complexities and all of these issues, but I imagine they're not easy. But certainly, from the agricultural standpoint, you could shift to different types of crops depending on the region, and shift to different times of the year. So you shift to a cooler time of the year. But for example, if you look at wheat, which tends to be a winter crop, that could get shifted out of the picture, say, for the Nile Basin, because it gets too hot there even in the wintertime.
Just one last question. Where is the business continues as usual? Where is the spot? What is the area in the planet that people would be able to live on? The last place.
Yeah. Yeah, I hate to talk about winners and losers, but certainly the further north you go or further south, depending on the hemisphere you're in, so I mean, yeah, there are certainly regions that you could imagine. There's already regions in the world that are uninhabitable at certain times of the year, and there's a potential for more of those regions to evolve. But if you go up higher in the mountain, obviously it gets cooler. If you go further, into Canada or something, or into the mountains of Turkey, you could gain refuge from the heat there. But you're isolated in a very small country, and it's difficult to escape from the heat. So I think.
Next question. Okay, if there isn't, I'll intervene for a quick question that's a bit more broad, if you allow me. Through the body of literature that you've been reading and researching, and through the research you've seen around the world with regards to climate change and water issues, do you think there's a climate change fatigue? And if so, would you bet the future of mitigating this real issue in the youth or the current status quo of the political systems around the world? Especially like when we look at the recent conversations and some countries pulling out of the global conversation of climate change and such.
Yeah, I think there is probably climate change fatigue, and certainly our media doesn't help things because they present the extreme cases. So I think that even though those cases could be valid, it tends to polarize at least in the United States, it's a very divisive issue, and it's very partisan as well with our politicians. I even myself, I never thought when I started doing this research, I thought I'd be out of business by now and shifting into different topics because, I think we've been saying the same thing for a long time, even going back to, say, even the first or second IPCC report, and the evidence just becomes stronger and stronger each time. And to show, to have higher resolution simulations, we get better and improved information, and our models are improving and all that. But we're not, in the end, we're saying the same thing we were saying 20 years ago or 25 years ago that we're saying today, just with perhaps more accuracy. And our data are getting better as time progresses, and we're seeing more of the impacts of climate change. In terms of the education approach, I think the younger generations, is probably the I think they're more open to they're more optimistic and more open to mitigating and looking for solutions. Not only from the climate change standpoint, but from other environmental issues. I mean, I'm sure even thinking about the water quality of the Arabian Gulf, they're probably more interested in putting in measures to protect or improve the water quality and protect the current quality.
Any other questions or? Okay, fair enough. Professor Jeremy, thank you so much for an excellent presentation, one of our really good lecture series. Thank you for coming all the way from California, and thank you for the audience for the really interesting discussion that we had. And it's a wrap for today. Thank you so much.